Hello everybody, welcome to our webinar. I hope everybody can hear me and at least the symbol beside my name indicates that the microphone is working properly. This webinar is part of a series of webinars in the scope of the METCO project in order to report regularly about the progress of this project. What the METCO project is, I will introduce you in a couple of minutes, and after that my colleague Tatiana and I will present you some details about the work of PTB in this project and what interferometric length measurement has to do with it. First of all, I would like to introduce myself. I am Guido Bartel from PTB. I have been working in the field of optical length measurement since 2006 here, and well, the first talk I present you a short introduction into interferometric length measurement in order to give you the basis for the second talk of Tatiana. Well, fine, let's start. What is the METCO project? METCO stands for Metrology of Electrothermal Coupling for New Functional Materials Technology. And the reason why this project was founded 2 years ago, or was initiated 2 years ago, is that in different branches of industry, for example, power and process industries, and also automotive and aero engine industries, and also medical applications, show the demand for high temperature piezoelectric materials. The reason is that currently available materials, or at least most of them, are not able to be operated in higher temperatures because the piezoelectric characteristics would degenerate if the temperature in the surrounding area of the material would lead to a degeneration of this piezoelectric effect. And that is why in the scope of this project, on one hand, the goal is to develop new materials which work at higher temperatures, and on the other hand, to develop the metrology technology for characterizing the these couplings, which are shown here in this triangular scheme. For example, you probably know the piezoelectric effect. If you apply a voltage to a piezoelectric material, you see a mechanical deformation, and vice versa. If you apply a mechanical force onto such a material, you can read out a voltage. Also, this effect is rather popular if you change the temperature and the material reacts with a mechanical deformation. But also in between these two effects there's a coupling. And all these three coupling effects have to be characterized for these new developed materials. And this is the main goal of the project. Therefore, we have a consortium in this project of several national metrology institutes from Europe, and also to universities, for example, University of Leeds, who is developing the material, and also one industrial partner from Germany. But today we focus on the role of PTB, and if you want to learn more about the other partners, I would like to refer to the website of the project, but also after our talks you have the opportunity to ask questions, and as far as I see, there are at least a couple of members of this consortium here available in the chat, so they can also answer your questions if Tatiana and I cannot answer them properly. What I also forget to mention is that this session is recorded, so if you don't remember everything which we are talking about now, you probably will have the opportunity to have a look at the recorded webinar. I expect that it is available via the website. But you can also go to the website and sign in for the newsletter in order to keep kept up to date. Well, PTB's role in the project is that we can use our knowledge in the field of interferometric length measurement, or better to say in this project, a length change, because we want to measure the effect of temperature changes onto these new piezoelectric materials in the temperature range from 40 is not correct, at least room temperature is better, say 20 degrees Celsius up to 200 degrees Celsius, and also with an electric field applied in the region from minus to plus 2 kV per millimeter. That means what we are investigating here in our lab is the coupling of the temperature and the mechanical dimension, and also the effect of an electrical field on the mechanical dimension of a sample material. That is the link to my first talk. The title is Imaging Interferometry for Length Measurement and the Determination of Thermal Expansion, and as I already said, this is the basis, or it should give you the basis for understanding the second talk of Tatiana. And let's start why we are with the question why we are usually interested in the length of a sample. Well, it is one of the legal duties of PTB as the German National Metrology Institute to provide the service of calibration of material measures. For example, these gauge block samples here on the right side in the picture. These are made from different materials and are being used for the realization and dissemination of length, the base unit of length, and they are used in the industry for comparison of length standards. But if we can measure the absolute length of a material, and if I say absolute length, I mean that we don't have to compare such a sample with another one. We really can determine the length of one body which we have. And if we have this length, we can also change the ambient parameters, for example, the temperature and also the pressure of surrounding air, for example. And we could also just wait a certain time and have a look on the temporal change of a material after it has been heated and cooled down again, for example. So the long-term stability can also be subject of the investigation. And that means we can characterize material properties such as the coefficient of thermal expansion, for example. And this is what is interesting in the scope of the METCO project, but you will see this in Tatiana's talk. I go on with some basic information, how we can determine the length by using interferometry. Well, you can think of using an optical wavelength as some kind of a ruler. Actually, it works a little bit different, but this is the basic idea. You have such a gauge block shaped sample which is optically contacted on top of a reference plate of the same material, and such a sample arrangement you can put into such a two-beam interferometer. Here you have a light source, most times a laser, and this laser beam is split by a beam splitter plate into two beam paths. One is the reference path and one is the object path with the sample inside. And due to this widened path, which is divergent first and then collimated, you can image the whole field of view of the whole sample surface. And by changing the length of the reference path, you can apply a certain technique, which I will explain in a minute, to determine the length of this sample, for example. And the theory behind this is that you express the length of the sample by a multiple of the used wavelength of the laser. And this multiple is distributed in one integral part of the orders of interference and one fractional part. And how you can determine this, I will show you also on the next slide. But just these two hints. The integral part can be determined either from prior knowledge, theoretical calculations, if you know something about the thermal expansion, for example, but also it can be determined by use of different laser wavelengths and by repeated length measurement, which is also used for the determination of the fractional part, which is the fringe offset between the sample and the reference plate. And by looking at coincident fractional orders, you can determine this integral part within a certain variation range. And if I'm talking about the fractional part of this interference, you can have a look here on this picture on the bottom right. There you see these interference fringes. Actually, this is a simulation, but maybe it makes the principle clear. You have, for example, this bright fringe here, and there's a certain gap or shift between the white fringe on this simulated sample body and on the simulated surface of the reference plate. And this is a measure for the fractional part of the length, which is in this formula here. There are, of course, also limitations of this technique. Most contributing is the quality of the optical components. Well, one part, for example, is this beam splitter plate. If there are differences in the refractive index in the material, this all has influence on the result. But also the alignment and quality of the optical wavefronts are influencing the result. And this is directly connected to the sample requirements, because if you have a sample which is not very parallel regarding the front and the back side of the sample, you would have a tilted fringe pattern, and this tilt is a systematic influence on the measurement result if it's too large. Also, surface flatness is important, and of course roughness, because you need a reflective surface in order to perform this optical measurement. Together with the alignment, you can get parasitic interferences, and of course also temperature measurement is important for length measurement, especially for materials which have a high coefficient of thermal expansion, because then the influence is larger. And if you are not working in vacuum, also the index of refraction of the surrounding air is needed in order to take this into account. Well, back to theory. This is the formula which describes a two-beam interference. You have the intensity, which you can read out by a camera, and this is calculated from the bias intensity of the two overlapping beams and the modulation of the interference pattern, in this case, if you use a coherent light source as a laser. But what I want to point out, in this formula you have, if you know this quantity from the measurement, at least the value of the camera pixel, you have three unknowns, and what you want to have is this interference phase in order to perform the length evaluation. So you have to use this so-called phase shifting technique, or you can use this phase shifting technique in order to evaluate the phase. And for instance, you can use this Carré algorithm. There are a lot of more algorithms, but I choose this as an example because it's one of the easiest ones. In this case, you use 4 equations because you have one quantity more, this alpha here, and this alpha is related to a phase step which is used during the measurement when you record a series of 4 interference patterns. You see here on the right hand side. And if you look now on one of these pixels here, for example here in the upper left corner, you see this mid-gray value, maybe this one here. You apply a phase shift in the reference path of the interferometer, for example. Then this fringe pattern shifts a little bit, then you get a darker intensity value, and if you apply the next phase step, you get again a gray value, and in the fourth image a brighter one. This is just an example for 1 pixel, but what you can do then is use this system of 4 equations in order to solve for the phi, which is the phase. And as you can see, these other quantities here are eliminated from this system, and you get the result of the phase. And this is what you need for the length determination. Here again another example from reality for this sample arrangement with different gauge block shaped materials. At first you acquire these phase shifted intensity frames. This is shown here in the on the right hand side. You see a series of frames in the same picture. You can use these phase shifted images in order to evaluate the phase map, and this is for this evaluation not the Carré algorithm was used, but a different one, but the result should be the same if you apply it properly, depending on the measurement procedure. And now we want to know the fractional part of the length of this sample, for example. And here you see how you can do this. You just define these small regions of interest, one on the sample surface and 2 beside the sample, and then you apply this simple formula. You take the average of these values on the reference plate surface. You just take into account a possible tilt of the reference plate by this average. And if you calculate the difference of the phase value on the surface of the sample and of the averaged phase value on the reference plate, then you get this phase difference, and this directly corresponds to the fractional order of interference of the length. And then the last step is just that you have to know this integral part of the length, and then you are done. It sounds very easy. Actually, you have to take into account a little bit more, but this should suffice for understanding the principle. Well, and when you have a series of length measurements with different temperatures, for example, you can do the following. You have a look at such a plot. This is length depending on the temperature, and then you can calculate the coefficient of thermal expansion depending on temperature based on your length values. This is only a very basic plot here, but it also should suffice to understand the basic idea, because this is one of this is the principle which we can use and which you can see in the next talk, also related to the determination of piezoelectric properties of the material. Here you see a sketch of the real setup. We have 3 laser sources with different wavelengths. They are listed here on the lower right side. And the laser light is coupled into a fiber, one after the other. And at the end of the fiber, the divergent beam is collimated and guided into the vacuum chamber, which has a diameter of approximately 2 meters. The beam splitter plate here in the center distributes the light into the reference path and the object path, and on the way back we go this way out of the vacuum chamber to the camera, which records these intensity frames of the interference patterns. And what you see here in the object beam path is a translation stage with different symbols for gauge block shaped samples, and they can be moved to both sides in order to be able to measure different samples in one, not in one go, but without opening the vacuum chamber. The principle of this interferometer is a Twyman Green setup, and what we are doing, instead of just having a look on single points on the surface of the sample, is that we image the whole field of view of the sample. And then we apply this phase shifting technique, which I've explained earlier, in order to get the length from these measurements. The measurement uncertainty under optimal conditions with regard to temperature stability and well, what else do we have? Alignment and the requirements on the sample preparation is then finally in the order of 1 nanometer or even slightly below. Currently we have different configurations which you can use to operate the measurement. The first one is what I've shown on the slide before, around ambient temperatures, say 10 degrees Celsius up to 50 degrees Celsius. We can use this translation stage as a sample holder, and then the whole vacuum chamber can be changed in temperature via a thermostat. And we also have developed in the past years a measurement path, which is an external module for measurements at cryogenic temperatures, starting at 7 Kelvin and then up to ambient temperature. This is already working. And what you will see in the next talk of Tatiana is the new developed module for measurements at higher temperatures up to 200 degrees Celsius. I don't want to tell too much about this because you will see more details in the next talk. So if there are questions so far, we can make a short break. Please use the chat window if you have questions now. Otherwise, you have the opportunity after Tatiana's talk, and then we can also discuss a little bit more in detail. So let me wait a few seconds if there are any questions. Okay, this doesn't seem to be the case. So I would like to hand over to Tatiana for the next talk.
All right then, welcome everybody. Also from my side, I'm Tatiana Krust. I'm working here as a postdoc researcher since 2 years now, working on the METCO project, and I'm going to talk about our contributions, especially interferometric length and strain measurements on high temperature piezoelectrics. Again, if you have any questions, please use the chat window to ask, and of course we have a lot of opportunity for discussion after the talk. So, as Guido briefly introduced, the METCO project is about functional materials and about characterizing the couplings between their electrical, mechanical, and thermal properties. And if we want to characterize them or find out what they are doing, for these two we have to make sure that we can heat the sample and see what any kind of temperature change will do to the mechanical dimensions, so just to see the thermal expansion in this case. We're aiming at a temperature range between room temperature and 200 degrees centigrade. And if we want to see the connection between the electrical and mechanical properties, so in this case the piezoelectric actuation, we have to be able to apply an electric field with voltages in the order of a couple of kilovolts so that we can reach maximum fields of 2 kilovolts per millimeters. So the first step in the project was to devise and fabricate a novel sample environment for this case. But before I'm going to introduce that in detail, I'm going to talk a little bit about the piezoelectric samples we are looking at, because in some ways they differ from the samples that Guido was talking about in his talk. So instead of any kind of gauge blocks or block-like samples, we have those small discs here. They have a diameter of 15 millimeters and a thickness of 2 millimeters. The polling direction, as indicated here, is perpendicular to the circular faces, and we chose this geometry for different reasons. One is that we have to measure it in different setups, so we are not the only ones in the project who are working with those samples. So every setup, every interferometer or whatever kind of setup we have has slightly different sample requirements. So we have to make a compromise that one kind of sample fits to all different setups. Also, this kind of sample shape is pretty well understood because it's a typical piezo sample geometry, for example, for resonance measurements. Another big difference compared to the gauge blocks is that we have to have electrodes to apply the electric field to the sample. So both circular faces, the top and the bottom, have to be metal covered with some metal composition. We are using a titanium adhesion layer and then 100 nanometers of gold roughly as an electrode, and this is what a microscope image of one of those samples actually looks like. This is just a requirement we have for the general sample geometry, but as a drawback, it makes the ringing contact, which Guido mentioned in his talk, impossible. All the other samples are rung to a reference plate just to measure the length of them relative to that reference plate, and this ringing contact is not possible in this case, because for one, it would damage the electrodes, and it also introduces some kind of mechanical constraint. And imagine if you apply a field to the piezoelectric sample, then the sample expands in the polling direction, and it also has to contract laterally, and this kind of contraction would be inhibited or disturbed by the ringing contact. So we had to find a different approach for the sample mounting. Okay, just a quick outline of my talk. At first, I want to give you some details about the high temperature sample environment. Then I want to show you some first results we got on PZT to show you that we can really do interferometry at high temperatures, and then a quick glimpse on the next steps and future plans we have for the project. So let's start with the sample environment. Just to remind you, this is again what the interferometer looks like, and the first question we had was, where do we actually put the sample environment? Guido mentioned that we have different possibilities, and we decided to build it as an internal module, as indicated here, which is placed inside the main vacuum chamber of the interferometer. And for that, we had to slightly modify the beam path compared to the usual gauge block measurements. So we are using these two additional mirrors to guide the light downwards to the sample, just to make use of the space we have in the vacuum chamber. And over here you can see a schematic of what the sample environment looks like. So we have our sample with the electrodes on both faces. This is placed on a 3-point support on a reference plate. Remember that ringing isn't possible in this case. And those two are sitting on a heating module, where the sample and reference plate are just heated via thermal conduction, and from above we can shine in with a laser to measure the interference patterns. And the entire sample environment is thermally shielded just to keep the heat localized and to make sure we don't have any damage to the surrounding components in the interferometer. So a little bit more detailed view of the sample environment is shown here. Again, you can recognize the sample disk in the center, then the reference plate with these gold stripes as a 3-point support. Then you can see those fastening clamps, which are used to keep the sample in place without constraining it considerably. And they also serve the purpose as high voltage contacts because somehow we have to apply the field to the sample. And below all of that, the heating module is indicated. So in the CAD of the sample environment, this looks a little bit more elaborate, but I guess you can recognize most of the crucial elements. Again, we have the sample disk, the reference plate with the gold pattern, those clamping arms with the wires going out here, the heating module, and this entire thing is surrounded by a METCO ceramic block, which is used to mount the individual components and also acts as a thermal shield because it has a low thermal conductivity. In case you're wondering how big is this is roughly 15 by 15 centimeters, so it's pretty compact. And in addition, we also use this gold-coated metal cylinder as another heat shield against thermal radiation. So the real thing looks like this. Again, you can see the sample, the reference plate, the clamping arms, the heating module, ceramic block, and heat shield. And now with this kind of sample environment, we're equipped to do high temperature measurements and also measurements at applied electric fields. And I'm going to present some results. For those first tests, we decided just to use a commercial flavor of PZT, in this case Noliac NCE80. We just thought that's easily available, it's not too expensive, we can play around with it, and if we break one, then it doesn't really matter. As supplied by Noliac, the curie temperature is roughly 300 degrees centigrade. The D33, the piezoelectric coefficient we're interested in here, has a reasonable value, so testing in the intermediate temperature range should be possible, let's say below 150 degrees centigrade. Before I present the results, I want to say a few things about the measurement procedure, because although it sounds quite simple, it's actually not really simple. So once our system has reached some temperature equilibrium, whether at room temperature or higher temperature doesn't matter, once it's in thermal equilibrium, then at first we have the voltage off, then we switch it on or ramp it up to some initial value, leave it on for some time, then ramp it down again, wait for some time, go to the next higher value, switch off again, go to the next higher value, and so on. And we do something while the voltage is switched on, and we also do something while it is switched off. While it's on, we acquire the interference images. Remember, due to this phase shifting technique, we have to acquire more than one image. So in this case, it's 10 images for the algorithm we're using. And this takes about 30 to 60 seconds, and longer if we are using 3 different wavelengths for the absolute length measurement. And then when we switch the voltage off, we use the time while it is off to store and process the data. So just calculate the phase map, check whether the phase stepping worked perfectly and everything. And this is just an example of what the phase map looks like, which is calculated from those interference images. This takes about 2 minutes at the moment. And then we repeat this for every voltage step we are looking at. And once we completed the voltage cycle, we can go to the next temperature. This takes about 24 hours to reach the next temperature equilibrium. There is still room for optimization, and we have some ideas what we can improve, but this was the measurement sequence we used for all the data I show you now. So let's start with something really basic. PZT NCE80 at room temperature, 20 degrees. The initial length of the sample was something like 1.8 millimeters. And here the length change relative to the initial length is shown as a function of voltage. So we start here at 0, then ramp the voltage up and see that the sample expands, ramp the voltage back down, see that it goes to 0 again, switch the polarity, go to some maximum value of the voltage, and go back to 0 again. So just to zoom in so that you can see what it looks like, and especially for the negative polarity part here, you can see that there is some kind of hysteresis behavior. This is again the same information, just plotted a little bit differently. If you're more familiar with this kind of representation, this is the strain shown as a function of the electric field. So strain and field are defined like this. It's the same information as before. And from these data, you can calculate the D33, which is just a rough estimation for the moment, and we get a value of roughly 270 picometers per volt, which agrees very nicely with the data provided by Noliac. So this is encouraging for some first results. But remember that we have an imaging interferometer. This was just one length value I showed you. In fact, we can see the entire sample surface at once and see what it is doing when we apply a voltage. So just to show you the sample surface deformation, I removed any piston type of movement and any tilt of the sample. Both are present as well, and the piston type movement is even the dominant part, but Just to make sure what kind of bending or deformation the sample does, I removed them because this effect is rather small. So the height scale here is just 60 nanometers peak to value. And I prepared some small movie where you can see how the sample surface changes when the voltage is changed. So we go up to some maximum value, back down to 0, to negative polarity, and to 0 again, and then you can see that there is some change in the surface shape. But it's not really dramatic, but nevertheless interesting that you can see that this kind of change is present. I just play the movie again so that you can watch it again. Okay, then let's do something more interesting. Let's go to higher temperatures. In this case, 100 degrees centigrade. It's the same sample, it's the same measurement scheme as before, it's just at a higher temperature. So again, this is the length change plotted as a function of voltage. We start from 0, go up, go back down to negative polarity, and in principle back up again. And already here you can see in the positive polarity part something like hysteresis behavior. Again, the same plot as strain versus field, so the same information. From the positive polarity part again, you can calculate the D33, which yields a value of 420 picometers per volt, which is larger than the room temperature value, but it's not really surprising. We don't have any value to compare it to because Noliac doesn't supply that, so we don't have anything to compare it to, but we can still measure it. And now maybe if you're wondering why this part here of the curve is missing, there's a simple explanation to that, because the sample broke during the measurement. You can see it here, that there is a bit actually blown away or chipped off at the edge of the sample, and probably that was some electrical breakdown during the measurement, and because of some high strain developed during that process, it just was blown away. So this in turn makes the change of height topography much more interesting than in the case before. Again, piston type movement and tilt are removed, so it's only the surface deformation, but notice the scale. This is almost 1 micron in surface deformation change now, and you can see it also in the movie I'm going to show in a moment, that the surface shape at the beginning and in the end of the movie look quite different, so there is really some big change induced, and this is due to the breakdown of the sample. Okay, now you can see it at the negative polarities, that somehow here this surface shape changes dramatically. Okay, I'm also going to play this one again so that you can watch it again. And this breakdown that we can observe is probably caused by some combined influence of the electric field and of the high temperature. So this indicates that this is really, almost the maximum temperature, or in this case, the maximum temperature for PZT, which was useful in this case. So I want to show you some next steps and future plans that we have. One thing is we're going to look at different piezoelectric materials, in this case bismuth ferrite perovskites. This is in close cooperation with the University of Leeds, who are also engaged in the METCO project. They are specialized in fabricating those materials, and the first candidate we are looking at is bismuth ferrite lead titanate, which has a Curie temperature of about 650 degrees centigrade, so operation should be possible up to 300 degrees centigrade. The only drawback that we saw was that we have a complicated sample fabrication process. We have to start with producing the green body, so those discs with 15 millimeters diameter, 2 millimeters thickness. We have to electrode them, pole them, so that they get their piezoelectric properties. And then in principle you could say, okay, now we go and measure them. But remember those tight sample specs regarding parallelism and flatness that Guido mentioned. We saw that the poling induced some dramatic change in the surface shape. So after poling, we have to remove the electrodes again, have the samples polished to the required parallelism, and then metal coat them again with our very well-defined electrodes that we need in the measurement. And this polishing is in progress right now, so we're just waiting for the first batch of samples to come back to us, and then once they are finished, we can do measurements on them. So if you want to know how this continues, just keep in touch. And of course, we can have a look at other piezoelectric materials as well, like quartz or crystal, gallium orthophosphate, lithium niobate, for example, or other ceramic compositions. So there is still quite a lot of work to do for us. And within the METCO project, we're not the only ones doing interferometry. We just introduced our imaging interferometer with our temperature range up to 200 degrees centigrade, but other groups like NPL are doing interferometry as well. They are equipping their German interferometer with a furnace so that they can measure their samples at really high temperatures, up to 1000 degrees centigrade. And also our industry partner Exact has upgraded their commercially available double-ended interferometer with a sample holder where they can reach temperatures up to 600 degrees centigrade. So we have quite a bit of overlap between those three systems. And if we measure the same samples, we should be able to compare our results, which is, should be interesting to see what comes out of this kind of comparison. So this is what we're going to do within the next month. And with that, I would like to conclude. I introduced you to our high-temperature sample environment to do interferometric length measurements on high-temperature piezoelectric materials. I showed you some results at PZT, for PZT at room temperature, for PZT at higher temperature, where we saw this unexpected breakdown of the sample. I gave you a bit of a glimpse on what's next, like other materials and comparison between interferometric systems. And if you want to know more about the METCO project, there's a couple of different ways. You can either have a look at the homepage here. You can find it at this address. Especially the news section should be interesting because there you find something like webinar announcements or what kind of conferences we're attending. You can also subscribe to the newsletter. Just write an email to this address and say you're interested. Or if you have any other kinds of general questions or comments, just write an email to that address. And of course, if you want to know more about interferometry or have any detailed questions, you can contact Guido or me directly. And with that, I would like to thank you for your attention. I would like to thank the EMRP for funding, and now I can only encourage you to join the discussion and to ask any questions you might have. Thank you.